you ready for more coordinate business? Oh yeah, first the homework stuff. The first homework is due today. Some of you already posted it, so that's good. Those of you who didn't, I hope you will do that soon. I already posted project number 1, which is important. That will be exercise for you on the coordinate transformations and affine transformations and all that. So you actually put all this stuff we were talking about here in practice. So it's already up on Canvas, so you can download it. There is again the instructions as usual, and the deadline will be next Friday, just like a week. Does that work? Hope so. So I figured I didn't do such a great job so far explaining the coordinate transformations, or there's probably no way of me doing a great job because the topic is slightly tricky, but I will still try once again to like give you my best way of explaining that. So I figured that to make you understand this better, I get to give you like a preview of inverse matrix, just like really a preview. We will then talk about inverse matrices in much more detail for general matrices, but I figured I can tell you already very easily what is it for a 2x2 matrix. So if I have a 2x2 matrix, and for 3x3 matrix is also very simple. Then the inverse matrix, like M inverse, is another 2x2 matrix, such that M times M inverse is the same thing as M inverse times M, and is this, which is what we call the identity matrix, and denoted with capital I. Now, of course, for n by n matrix, the definition would be exactly the same. So the idea is that we know that a matrix represents a linear transformation, right? And the inverse of the linear transformation would be represented exactly by the inverse matrix. Maybe I will give you an example on matrices, on rotations. In rotation, it's fairly clear what this means. If it became blurry, then just yell at me and I'll try to fix it. I don't know if this is ideal. Yeah, good. So one thing too, you can immediately notice that not every matrix has an inverse. It would be sort of nice if every matrix had an inverse, but it's not true, right? If I take, for example, this matrix, there is no way I could multiply it with some other matrix so that I would get this back, right? Because when there is zeros here, there is no way I could get the 1 here, right? There will always have to be 0. So this matrix, no inverse. And we will discuss this in hideous details later. Good news is that rotation matrices are our friends. So 2x2 rotation matrix looks like this. You should remember this by now, right? So it's parameterized by the angle of rotation theta, and it's a matrix like this. So I can call it like r theta. And the inverse of the rotation matrix, not only it does always exist, but also has a very simple form. What would you guess would be the inverse of that? R theta inverse. It's not that difficult to guess. You have one try. Yeah? Or it is still a rotation matrix. Yeah, that's the first very good observation. So inverse of a rotation matrix will still be a rotation matrix, yeah? And by which angle?
By 316, or
yeah, just my minus theta. Exactly. So the inverse matrix of r theta is just r of minus theta, or I can write it like this, whatever, really, right? So that would be cosine. I'll do it pretty slowly here. Sine minus theta, minus sine minus theta, and cosine of minus theta. And then let's recall some very basic trigonometric properties. So cosine does not care about the sine, right? So it's just cosine of minus theta is just cosine of theta. Sine does. Sine takes the sine. It's sort of funny in English, but that's, yeah, so I hope you understand me. So this is the form, right? And you can easily verify that this indeed is an inverse matrix. So this is the r theta. I'm just copying it here. So this is just r theta. And I copy here the r minus theta, and we try to multiply it to see if it really is the inverse, which it should be, right? Intuitively. So this is r of minus theta. So if you do the multiplication, you should now remember how matrix multiplication works. So the first element here, so there's 4 elements, right? For the first one, I have to do cosine theta times cosine theta, so it's cosine squared theta, plus, because there are 2 minuses, sine squared theta, right? Cosine squared plus sine squared is 1, right? The second element, I'm multiplying first row times the second column, so it's going to be cosine theta sine theta and minus sine theta cosine theta. So that just subtracts, and I get 0. And same thing happens here. Sine theta cosine theta minus cosine theta sine theta, so I get 0. And you can see where it's going. Sine squared here, cosine squared here, I get 1. So if you have the good mental picture of matrix multiplication, you can immediately verify that. And if you think about it, this is like the geometric intuition would be like this. If I have some vector v, and I first rotate it by theta, and then rotate it by minus theta, well, then I of course have to come back, right? If I rotate it first there, rotate it back, I'm back to my vector v, so I've done nothing. So this is minus theta. So this means that I first rotate, and then first rotate by theta, then rotate by minus theta, I am back, right? Due to associativity, now here you can see how deep the associativity property is, right? Because due to associativity, I can write this, r theta v, and what I have just computed, r theta times r minus theta, this is just identity, right? So this is just identity times v, right? If it's the first time you see the identity, which I doubt, then I could write it like this. From this, you obviously see that the identity matrix does nothing. It just lets the vector through without making any change. Yep. So in general, if you think about it as transformations, so matrices are the special case that they are representing linear transformations, right? You can think about functions in general. If I have function, it doesn't even have to be between vector spaces. It could be like any sets, right? If I have function mapping from v1 to v2, then the inverse would be mapping from v2 to v1, such that when I compose them, I get identity mapping. I go back, right? So the picture would be, if this is my set v1, and it can be a vector space, can be something else. The inverse function is more general concept than that, right? Then I have some v2, and I have something maps here by f, then the inverse has to take the same thing back, f inverse. You probably know that the inverse does not always exist, right? It has to be injective. Have you had this thing somewhere in mathematics? What is injective function? Yeah. Okay. So I will not do that. So the inverse is unique and exists if f is bijective. The matrices make it simpler because they don't deal with general functions, but only with linear transformations. So let me repeat once again so you remember it. Every matrix represents a linear transformation, and the inverse matrix represents the inverse linear transformation. So going the other way around, going back. So this is my quick 5 or maybe 10-minute introduction to inverse matrices. And now let's go back to change of coordinates. I'm basically trying to make your life with the project number 1 easier by giving you my best attempt to explain the change of coordinates, because that's what most the project 1 will be about figuring out change of coordinates, right? I thought maybe I can do like a motivational example first. We talked about these things like this. And if like a problem in robotics, and there is some fixed base, and then there are some moving rigid links which are connected with joints. These guys are joints where the links can rotate. These things are like rigid, you can like steel blocks don't ignore the fact that here they overlap, but they couldn't. It's just like a mathematical model for a robot. That doesn't really matter. And if I have a coordinate system A, it's very easy for me to figure out what are the coordinates of this block in A, right? If it's like 3 units or 2 units long and like 1 unit thick, then this would be like 2 and -1, right? This would be like 2 and 1, and so on. So figuring out the coordinates of these points with respect to A is trivial. Right? What I need to be able to draw it or do anything else with it, but in your project we'll be actually visualizing it in MATLAB, drawing these things. So what I need to draw it, I need to get the coordinates of the same points with respect to G, with respect to some world coordinate system, the coordinate system of the base. This is the base, which is fixed. Or with respect to a screen, with respect to a camera, if you want to render it on a camera. Okay. So, change of coordinates. And we will start first with just the linear or vector space. Linear space. Linear space and vector space, that means the same thing. I don't think there is usually any difference. So let's look at an example. So for this time, for a moment, you can forget about the affine spaces. So let's go through slowly how the change of coordinates works in linear spaces. Because then in affine spaces, which we'll really need, it's the same thing appears there plus translation. So let's deal with this case first. So let's do an example. So I'm in a linear space, so I have my 0 here. That's the origin of everything in the linear space. And this is one set of basis vectors. So that's vector xi, ya. And let's say I have another basis, which looks like this. This would be my basis b. This would be xb vector. And here I would have vector yb. So I give it these arrows to make it clear that these are vectors. This is the same thing. I just made a little gap there so you can like see that these are two arrows, but they are at the same spot in space. So let's say I have some vector here. So we are in R2 here, right? Let's say I have some vector p. For example, here. I can measure the coordinates of P with respect to either of the bases, right? So the way I draw it here, I think, so for this example P, the coordinates of P, or let me first do it in general. The coordinates of P would be PAX, PAY, right? And with respect to the system A, and with respect to the, or basis A, and with respect to B would be PBX and PBY, right? So what that means is that if I can reconstruct the vector P, those are also vectors. And those are not, those are scalars. That's why I don't give them an arrow. So I can reconstruct the vector P either in the basis A or in the basis B. So if I do it in the basis A, it's PAX times XA plus PAY times YA, right? So what would it mean in this example if I pick this vector P? I mean, this works for any P, right? But if I pick this particular example, P, and this particular example of basis vectors, then what would the PAX and PAY be? Can you tell me that? What would be the actual numbers corresponding to this drawing? It's always good to give it like some example and give actual numbers so you can get an idea. So what would be PAX? So I'm projecting this vector onto the XA vector, right? Any guess? Just shout. Huh? Negative what? Negative 1, right? So for my example, this would be -1 because I go 1 unit here, right? And then I go 1 unit up, so it would be -1, 1. That are the coordinates with respect to the basis A, right? This is the XA vector, so I have to go against it, and then I need to add 1 vector YA to go back up, right? How about the b coordinates for the same vector? So p is still the same vector, but now I'm looking at its coordinates with respect to basis b. So what would be the coordinates there? 1, 1, exactly. All I need to do is take one vector yb, one vector xb, add them together, right? So the same vector, it's always the same vector in both cases, except that it's expressed in different coordinates with respect to different bases. That's the point I really want to make in this lecture, so you get it. So I can either express the vector p using the basis x vectors, the xa and ya, or using the basis b vectors, xb and yb. Because those are different bases, in both cases I will have different coordinates, as you see here. Those coordinates are not the same, even though the resulting vector is the same. That's because the bases are different. That's really my frame of reference, right? Now, my question is, I want to be able to convert between the two bases. So if I have the coordinates of the vector with respect to basis A, I want to be able to convert to coordinates in basis B and the other way around. So how do I do that? I'm very grateful for the matrix multiplication because this lets me write this equation in this form. xa ya times bax pay, right? Or this would be just be a vector, right? The same way I can write this as xb vector, that's like a column vector, and yb vector. And times pb vector. Oh, looks nice. So this is matrix vector multiplication. Those are like 2 by 2 matrices, these things, and they are multiplied by the coordinates. Now, because the p is the same, then that means that this thing has to be the same, right? That the matrix xa ya times pa, I'm just copying this thing, is the same as xb yb pb, right? Because in both cases it's just p, so those things have to be those things are the same thing. And from this I can derive the matrix which will be converting the coordinates. Here is where I need the matrix inversion, right? So if I want to convert from coordinates A into coordinates B, I have to invert the first matrix. I do xa ya inverse times xb yb pb. Right? So what I did here, I took the xa ya inverse and multiplied both sides of this equation from the left by that inverse. Because it's inverse, here it disappeared. Here I got just identity, which I don't even have to write there because it does nothing, right? And here I have the inverse. So this matrix is the change of coordinates from coordinate system B to coordinate system A. PB are coordinates of P with respect to basis B. PA are coordinates of the same vector with respect to basis A. And this is the matrix which converts between the two bases. Right? Are you happy? If I want to convert the other way around, then obviously what do? I multiply by the inverse of this matrix, right? So the result I would get would be xb yb inverse times xa ya pa equals pb. And I owe you some arrows here, like this. So now this matrix is converting from coordinates A to coordinates B, or from coordinates with respect to basis A to coordinates with respect to basis B. So let's look. It's always very good to look at an example. So let's look what it means in this example, right? So what is my xa and ya? Well, I chose it here so it's simple. So it's xa and ya are just the standard basis vectors. So let's plug in the actual values here. So here in this case, for these two bases I have drawn in this example, the xa is just 1, 0, and y is just 0, 1. Inverse. And what is xb and yb? So xb is what? It is 0 in x and 1 in y. And yb is -1 in x and 0 in y. Right? So those are the coordinates with respect to the standard basis vectors corresponding to this drawing. So this is just identity. So the inverse of identity is, of course, again identity, right? Nothing happens there. So I can just take this away, and this is the conversion matrix. So this is the matrix that converts PB to PA, and we can test it. We can try to plug it in. So let's try. So we know for this vector P, it has B coordinates 1, 1, right? So let's try what happens if we do this. That's why the MATLAB is such a fun thing, because it does all these matrix calculations for you. So this is my conversion matrix corresponding to this drawing. This is my coordinates of P in B. So this is my PB, and what I get is -1, 1. And that is exactly, as you can see here, the coordinates of P in A. So indeed, this matrix does work. And it would work the other way around too, the inverse matrix, right? So one thing you can notice, what is this matrix? It is actually a rotation matrix. If you look at, again, let me put here the rotation matrix again. This is the general form of a rotation matrix. So guess what? What if I pick theta equal 90 degrees, right? What do I get for theta equal 90? So cosine of 90 will be 0. Sine of 90 is 1, but there is minus, so it's -1, and sine of 90 is 1. So that's exactly this matrix. So this matrix is nothing but rotation by 90 degrees, right? And you can sort of see it from this drawing visually. You can also imagine like the linear transformation as like acting on the space. So if I rotate, vector xa rotates onto vector xb, 90 degrees rotation, counterclockwise. Always the default is counterclockwise. And ya rotates on yb, also 90 degrees rotation, right? If I wanted the opposite transformation, if I wanted to go from PA to PB, so if I wanted this matrix, then I can again substitute, plug it in here, and I would get, I have to get the inverse, right? So the inverse of this matrix, what would be the inverse of this? Let's see if you are paying attention. Yeah, so rotational about -90 degrees, right? And if I do the math, I get it's exactly minus this matrix, turns out. So it looks, it's basically flipped. The -1 went here and the 1 went here. That's not a coincidence. That's actually generally true for rotation matrices, but we will save that for later. Okay, so and here is the most important conclusion. So if I have a rotation by 90 degrees, counterclockwise rotation by 90 degrees, this is the matrix of that rotation. So it maps the vectors from basis A to basis B, right? If I rotate this XA by 90 degrees counterclockwise, I get to XB. The same thing for Y8 going to YB. So this rotates one basis onto another. If you want to look at the transformation as like taking the space and transforming it, that's one way you can look at it, right? The other way you can look at it is as a coordinate transformation. So maybe I will write it down. R90, you can see it. maps or rotates basis A on or onto basis B. The other thing the R90 does is it converts coordinates from basis B to basis A. And this switch is what I really want you to remember. This is not a mistake. If the basis moves the basis A onto B, then it converts coordinates, but the other way around. Converts coordinates from B to A. Because here, right, this is my R90. It takes coordinates with respect to B, returns coordinates with respect to A. If I want to convert coordinates the other way around, I need to ask for the inverse matrix, right? I need to do R minus 90, and it then converts the coordinates from A to B. So this is good to remember, because otherwise it can generate some confusion, because it's not the same thing. You can think about transformations two ways: either transforming the space itself, or performing change of coordinates with respect to bases. So the space is not changing, but I'm just like looking at my vectors or points with respect to different reference frames, with respect to different bases. And these concepts are inverse one to each other. So that was the point of this example. So if you only want to remember one thing from all this, remember this. If it maps from A to B, then converts coordinates from B to A. So this was just the linear case. You will need to deal with affine case, because we need translation, right? And so I was saying we cannot directly do translation in a linear. The translation is not a linear transformation, so I need to go to affine space. So remember, if we are in affine space, then instead of vectors, we are dealing with points. And if we are doing it with the homogeneous coordinates, we just append this one. So those are points. And we still have vectors in the affine space. They sort of correspond. Vectors are not directly in that space, but you can imagine them as points at infinity. That was the projective plane. I don't want to repeat the whole thing again, but vectors you can represent in homogeneous coordinates like this with 0. And they are not points. Points have to have their 1. Yeah, we have been through that. So then affine transformation always has this structure. If I have an affine transform in homogeneous coordinates, I always write it in this block structure. So here is my translation. Here is 1, here is zeros, and here is the linear part. So in case of two-dimensional space, this has just two. This is a 2 by 2 matrix. There I have 2 zeros, and I have 2 translation vector coordinates. So let's do an example. So similar example to what we did for the linear space. So instead of bases in affine spaces, I have coordinate systems which are bases with a reference point, right? So for my basis A, I will call the reference point just A, and I still have some basis vectors X, A, and Y, A, and I will pick a different coordinate system here. This point will be called B, and I have it's only a simple example, but you will already see how it works there. And these 2 points, so if you should remember, if I subtract 2 points, I get a vector, right? And this is a translation vector. So these 2 frames, or coordinate systems are sometimes called frames, they differ only by translation t. And then if I have a point, so now I'm measuring coordinates of points, not of vectors, because I'm in a defined space. So let's say I have points somewhere, for example here. So if I want to express the coordinates of P with respect to the frame B, then I start with the point B, and then do the same thing as I was doing before. So I take PBX, that's the x coordinate, and I add the vector x, I multiply by the vector xb, and I add pby times yb. So I could also write it in matrix form. So here is my point, and here is my xb, yb, and this is the coordinates of the point. So this is exactly what we have seen before. The only difference is that here I'm adding reference point B. The same way I can represent, again, it's going to be the same point, but now with respect to the coordinate system A, right? So I start with point A, and I add PAX, that's the x coordinate, with respect to vector XA, plus PAY, YA. And again, if I write it in the matrix form, which is really much more elegant, I hope you will learn to appreciate it. It looks like this. You know that this thing is xb is a vector, yb is a vector. If this is also like a two-dimensional thing, the points, right? The dimensional is the same, but I don't give them a row because to differentiate between points and vectors. And you know that if I add a vector to a point, I get a point back. So everything is correct. So then I can do the same thing as I did before, right? These two things have to be the same. It's each way I get both. I get to the point P, just like I get to a different way every time. So these things have to be the same, right? So that means that A plus XAYA PA is the same thing as B plus XB YB PB, right? Now what I'm trying to do is to get analogous formula for change of coordinates in affine spaces. So if I have the coordinates of the point with respect to one coordinate system, I want the coordinates of the point with respect to other coordinate system. Here it's going to be just slightly different because the coordinate system here differ also by translation, right? In this case, this could also be rotated, right? But just for simplicity, I just did not rotate it, because then we can deal with composing things by composing the matrices. So if I want to convert the coordinates, that's simple. The first thing I can do is this. I can say that this is B minus A. And what is B minus A? I'm subtracting 2 points, which is valid, and the result is a vector, right? And this is exactly this translation vector T, right? That's the difference between the two origins. So if I want now to convert the B coordinates into A coordinates, all I need to do is again invert this first matrix. So XA YA inverse times T, plus again the inverse XA YA inverse XB YB, and B coordinates are right here. So this is just a 2x1 vector, or just a two-dimensional vector. What actually, it's good to like think what this means. Those are the coordinates of the vector T with respect to the basis A. Right? That's what it means, the inversion. And here is a standard 2x2 change of coordinates matrix. That's the same thing we had before, right? Remember that. That's the linear part. The affine transformation really has just two parts: the translational part, that's this thing, and the linear part, which in this case is rotation. In this case, it's just identity because I did not rotate at all, but I could rotate the other system. It would not be identical. So in this specific case, it's very simple because both XA and YA and XB and YB are the standard basis vectors. So in this case, all the matrices are identities. So all I'm left, in this case, the corresponding to the drawing here, all I'm doing is this. I'm just adding the translation vector t. In general, if this rotated, it would not be so simple. Also, the A system would not have to be the standards. It could be also rotating, right? So if you want to better understand it, you can try variations of these examples, do them by yourself. You will have to do a similar thing for your project. So this is the way to actually understand it. So you should remember from before, I said that instead of adding vector t, which I don't really like the addition there, I would rather do matrix multiplication, because then I can collapse all the matrices together. I just multiply them all together. So instead of doing this, I can use the homogeneous coordinates trick. I can just give it the extra 1. And here I use the homogeneous matrix corresponding to a translation, right? That's what we were discussing the last time. PBX, PBY, and 1. And that's the same thing. This equation says the same thing as this. Here the last row is basically bogus. It just says 1 equals 1, right? Sometimes people like ignore the last row and just write it like this, but it's sort of nicer to keep their like 3 by 3 matrices, because then it's nicely symmetric. And again, you can notice the same thing as I said before about transforming from A to B and B to A. So let's look at it in this affine case. It works the same way as in the linear case. So I can look at the affine transformation 2 ways. Again, this is important. So either I can look at it as transformation of the space, right? That I have some points here that map somewhere else in the same space. In particular, if I want a transformation such that the basis A, or the coordinate system A, maps onto the coordinate system B, like if I take this and translate the whole thing, then this is just at t, right? This is exactly this transformation describes that, right? So this performs translation or motion from A to B. If I want to change coordinates, I have to go the other way around, because the same matrix changes coordinates from B to A. That's what's written here, right? So the matrix, if I apply it to some point, it moves it by t, and the change of coordinates changes, but the other way around. If I wanted change of coordinates from A to B, what would I have to do? What sort of matrix do you think would do the trick? Yep. Correct. That would be this is M, the opposite conversion. I'll write it here. So this is PB vector 1. I write it slightly differently just to give you some notational exercise. That would be the inverse of M. And how would it look like for this case? In this case, it's again very simple if you think about it geometrically, right? If I translate by t, how do I undo the transformation? Negative t, exactly. 1, 0, minus tx, 0, 1, minus ty. That would be the inverse. And you can verify that if you multiply the guys together, you have to get identity. So again, I will not write it again, but I will just say it one more time. That if you translate the space such that it maps the frame A to frame B, then it converts coordinates from frame B to frame A. And if I want to convert coordinates the other way around, I need to take the inverse matrix. All right. So this was as good explanation as I could give you. You will really only understand it after you actually try to work through an example. So that's what the project 1 is about. There is a couple slides which say how to generalize this to 3D, but I think that's relatively straightforward, right? So it's always talking about R2 and doing homogeneous coordinates, that from R2 you go to R3. If I'm in 3D to begin with, if I have a 3D linear space, I'm going to construct a 3D affine space, the exact same trick applies. It's just a little bit more difficult to visualize because now I'm dealing in 4-dimensional space and sort of difficult to imagine. But the mathematics works exactly the same. I just add the extra homogeneous 1, and I form a 4-dimensional vector. So this represents now a point in 3D affine space, and this would correspond to a vector in a 3D affine space, or a direction vector, whatever you want to call it. So that's basically literally translating in 1 dimension higher. 3D rotations are a little bit more, well, actually quite a bit more funny than 2D rotations. Because in 1D, in a plane, I could always rotate, there was only one axis of rotation I can rotate about, right? This axis of rotation going out of the plane. In 3D, I can rotate about many different axes. I can pick any axis and I can rotate about it in 3D. It turns out that any 3D rotation I can compose from rotations about the basic axis, about the x, y, and z axis in 3D. We will talk more about rotations later, so don't worry about that. Here is the form of the rotation matrices. So you can see rotation about x leaves the first coordinate, the x, intact, right? That's the point. The points on the rotation axis, they don't move. The rotation y, same thing, leaves the y intact, and z goes about the z axis. There is one funny thing you might notice if you are looking carefully at these matrices. What is one funny thing you are noticing? Yeah?
The y-axis, the negatives on the side are reversed.
Exactly. And do you have an idea why is that? This has to do with the right-hand rule convention. So that's the usual convention, that if we are rotating, by default in mathematics, we are rotating counterclockwise with respect to the right-hand rule. That means if you put your thumb along the axis you are rotating, then you are rotating this way, in the direction of the fingers. So in 2D, there was really no confusion, right? If I had my x and y in 2D, then the counterclockwise rotation, the right-hand rule, always had to rotate this way, right? So in 3D, I can have two types of coordinate system. If I assume the right-handed coordinate system, x, y, and z. So it's right-handed because if I put my thumb along the z-axis, then I get a counterclockwise rotation from x to y. That's why it's right-handed. So this is a right-handed. That's what we usually assume we have. Now there could also be a left-handed system in some, like I think DirectX or something like that uses left-handed thing. It's to make things confusing, I suppose. The left-handed would look like this, right? The z-axis would be pointing in the other direction. This would be, I only put it like here because I don't want you to think about it too much. I wanted to explain why the y rotation matrix is different. Because, look at it. So the first rotation rotates about the x-axis, right? So it needs to rotate this way. It needs to rotate y on z if it's a counterclockwise rotation. The rotation about the z-axis, the third one, it's also fine because it does the standard 2D rotation, right? You can see it from the matrix very, very clearly. This is a standard 2D rotation, and this is just letting the z-coordinate through. But if I want to rotate right-handed about the y-axis, I have to go this way. I have to go actually from z to x, right? That means going the other way around than from x to z, and that's why there is the minus. You sort of have to think about the right hand, how it fits there. So the minus is there only so that this matrix corresponds to the right hand rule. So it rotates. If you put your thumb here, I need to rotate this way, and that's what this matrix does. Okay, let me try to finish this. So this is just linear transformations. If I want to move to affine transformations, all I need to do is append this row of 0, the column of zeros, and the last homogeneous 1, right, to all of them. So this is just copied. The linear parts are the same as on the previous slide, and the only thing is like this like frame by zeros and 1. This is following the general structure here, which I draw here. Here is the linear part, the translational part, zeros and 1. If the translation is 0, I have zeros here too. The zeros here are zeros all the time. Obviously, translations in 3D, I'm pretty sure you could guess it, right? So those would be the translation matrices in 3D, represented by 4x4 homogeneous matrices. And the effect of this matrix, as you can again easily verify, matrix vector multiplication, is just adding the vector t, doing it through multiplication. Scaling is also simple. All you need is a diagonal matrix. Those are the scale coefficients in x, y, and z axes. So I don't think that's worth spending time on. The one more thing you will need is a perspective camera model. That's the cool thing about homogeneous coordinates. We can also relatively simply represent their nonlinear transformation. Perspective projection is a very important example of nonlinear transformation. We normally don't like nonlinear transformations, but sometimes we just have to deal with them because that's what happens in a camera. So let's assume this camera model. There's like zillion camera models before. There was like this z-axis pointing the other way around, and it was like in -1. I made it a little bit easier that the z-axis is pointing to the right, and the camera plane is defined by equation z equals 1. And the projection, so this is the 0 here is the center of the camera. And I'm projecting an arbitrary point with coordinates xc, yc, zc onto the camera plane. I need to compute the coordinates uv on the camera plane, which correspond to the projection of this point. So there's like a ray of light traveling through the center. Somewhere it hits the plane. And the coordinates uv, where it hits the plane, that's what I want to compute. Right? It's very simple to compute because all you need to do is find a t such that xc, yc, zc will be equal to uv1. So that means that t zc has to be 1. So that means that t is 1 over zc. If I plug it in there, I will get that u is xc divided by zc and v is yc divided by zc. That's the formulas you had here in a little better font. My handwriting would be better if they finally got me the chair, but it's not happening still. So the perspective projection is a non-linear transformation, but you can do it. You can almost represent it as a linear transformation. That's what's happening. That's what's being done in graphics all the time. It's called the Z divide thing. So I can represent it by a homogeneous matrix if I allow myself one divide. So the whole nonlinearity collapses to one divide. And the perspective projection matrix consists of this linear part. So if I take x, y, z, and 1, so this is the magical matrix, which almost does a perspective projection. What it does exactly is gives me x, y, z, z, right? And then the only thing I need to do is a z divide. Divide this entire vector by z, because then that gives me x divided by z, y divided by z, and here I get 1 and 1. So now this is a valid point. It's a point on the z equal 1 line, and those are just the projection so those are just the coordinates on the plane, on my camera plane. So the only nonlinearity is here. Only nonlinear here. And the nonlinearity is just z divide, so it's not so bad. I can also have orthographic camera model. That's even simpler. Orthographic camera actually just is a linear transformation because the rays are parallel. All the rays are parallel. So I can represent it with this simple matrix, or fully in homogeneous coordinates would be this matrix. Would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. So here is where the magic happens. Or no magic, I just discard the z. Right? That's what happens there. So this would be the orthographic camera matrix in homogeneous coordinates. if you are programming like in OpenGL, then these matrices are exactly what you are passing the graphics pipeline, except that maybe the conventions might be slightly different. Okay, I have to finish here. I just want to give you a glimpse of the project number 1. This is what you will be doing there, like a little robot thing, where this is a fixed base, and those are some moving links. What you will have to figure out is the transformations, so you can actually draw these links on the screen. So read through this thing. It's on Canvas, and there are some MATLAB scripts to get you started and instructions what you should do. All right. Thanks a lot.